Hello. So this is me kind of showing off my. There we go. Sorry. This is me kind of showing off my wonderful computer that I made in this simulation software called Virtual Circuit Board. Looks really nice. It simulates logic gates. It looks really cool. There's no kind of abstraction aside from, abstraction. This is a fully functioning chip. The memory is handled by the software, so there's a bit of a virtual memory. So there's no memory storage because I'm too lazy to implement that really. There is a built-in assembly thing here with custom-defined symbols and everything, but I'll get to that later. So quick tour. Ignore this for now. Over here we have our clock. This little red thing is a clock, and this delays it so it doesn't tick every single tick, because that's too fast. This sends out different pulses at different times in the clock signal. I'll show you later when the thing's actually running. This is whether the computer is actually running or not. And then this orange line goes throughout the computer and, handles everything that needs timing, which is mostly writing to registers, right? Over here, this keeps track of the clock cycle of the instruction we're on, because instructions take, more than one clock cycle to execute. So it keeps track of which one. It'll increment 1, 2, 3, 4, 5, whatever, up to 7. But it normally gets reset before that, right? Here we have some control lines over here to deal with stuff. Over here we have our instruction register, which just stores the current instruction we're working on. And you can see these green lines go over here, up here, so we can actually execute instructions based on, which instruction we're on. Right below it, the program register or program counter keeps track of where we are in the program. So it keeps track of the address at which we're executing. This blue line right here, it's to increment the program counter. It's built into the register, so you don't have to do weird stuff with the ALU over here. I'll get into that in a second. So this is an auto-incrementing register. This right here is how we deal with memory. So you write a value to the address, and it stores it to this register automatically, or vice versa. You write something to this value register, and it puts that into the address. Right over here, we have our stack pointers. This is our function stack pointer and a variable stack pointer. So if we ever want to call a subroutine, we need to keep track of where we jumped from. So we put that in the stack, and we keep track of where the stack is by this function, or by the stack pointer right here. There's two lines to increment or decrement it, depending on what we want. And we want to store the functions separate from where we store the variables, because the user can also put something onto the stack and remove it later, and we don't want to mix that up with where the functions are. There's a different one, so you notice that this one starts at address somewhere, and then this starts at a different address. Wonderful. Over here is our ALU. So over here we have our A register, and down here we have our B register. So these are the two internal registers for operations. Most of the stuff happens in the A register. Some stuff will happen in the B register. You can move values between the two. And then in here is our ALU. So what it'll do is it'll take the value that comes from the A register and the B register and do a whole bunch of operations on it. So it will not the A register, so invert the A register. It will AND the A and B register together. It will OR the A and B register together. It will XOR them, and it will NAND them. Also, it will add them or subtract them depending on how it's set and configured. And then using these control lines over here, we can control what we actually wanted to output onto the green. The green is what we call the bus. It's where how components transfer data between them. So if a component wants something, it will write it to the bus. Or if it wants to give something, it will write it to the bus. And if it wants to take something, it will read it from the bus. So like the ALU will output its result onto the bus, which will then be read into the A register from the bus. These two down here are for output and input. So you can get values from the input or write values to the output. There's nothing connected to them yet, just because I haven't done that yet. And this is the flag register. It's a bit complicated, but sometimes your number is negative, sometimes your number is 0, sometimes there's a carry after you do a mathematical operation, and we store that in these little registers right here just to keep track of it, so we can do some conditional jumping or whatnot. All of these lines over here are control lines. That's not true. These are control lines. These are informational lines. So we have two sets of rows here. We have our condition lines. which gets our conditions, which are the instruction number, both inverted and not. We have our clock cycle number, inverted or not, and then we have our flags, inverted or not, and we can choose to execute or not execute instructions based on that. And then we have control lines, which is, read registers, write registers, ALU functions, other various functions, and then this one thing, which is just to read the flag register. It was added an afterthought, so that's why it's just going over here. And we have, since I ran out of space over here, we have the same thing up top. And this right here is technically, the quote-unquote brains of the computer. This is where all the instructions are stored. And there's a bunch of different instructions. The 3-bit, the 3-digit, the 3-letter opcode is up here, so we know what we're talking about. I'm just going to go over the simplest one. All the others derive from this. So here's some labels, so I know what's where. And this is the no-op instruction, which is run after the end of almost every instruction, because all it does is increment the program counter, write it to the address, and then write the value at that address into the instruction register so we can execute the next instruction. So what all these red things are saying is basically, if the instruction number is 0, and we're on clock cycle 0, because this is the first clock cycle of that, if that's all true, then turn these lines on. So what this line will do is increment the program counter. C is the second line from the top. That's incrementing the program counter. This line is the fourth line from the bottom. That means write to the address register, which makes sense. And we also want to read the program counter, so it puts it out onto the bus. This all happens at different times during the clock cycle. It doesn't happen all at once. So first the program counter is incremented, then we read all the registers out onto the bus, and then we write the bus into any registers that want it. Right, and the next thing we do, we clear this count. So this is on in 1 now, so see how this is 0, this is now 1. So we clear the count, so we reset this counter back to 0. We write to the instruction register, and then we read from the value. So we read the value and write that into the instruction register. All of the instructions do basically the same thing, just they do different things. This is called the microcode, so we translate the op codes into microcode and whatever. Now, I also have these purple lines, which normally aren't used, but they are used for the conditional jump instructions, which is really important because that's how the computer is Turing complete. For example, the jump if 0 instruction. Basically, if the 0 flag is set, we jump to the given address. Otherwise, we just skip this instruction and move on. This is why the computer is Turing complete. This and a couple others. So you see, it does the exact same thing. This is the instruction number. I don't remember it off the top of my head. This is the clock cycle number. It's 0. This is 0. And then also we read from the 0 flag. And if that's all true, then we execute all this fun stuff and whatever. Now, because we have the option to not jump, we also have the not jump 0 instruction. So see how this is this line, this is right below it, which is the exact opposite of that, right? So what this will do is it'll just skip the instruction. That's basically all it does. Oh, why is this here? This doesn't need to be there. Sorry, hold on. That was just, I don't know, it was just useless. Anyway, enough explaining, kind of boring. I'm just going to show you in action. So what I've written right here. So here's all the definitions of the instructions. I'm going to go over them really quickly. What this is saying is basically all this is a advanced way to write stuff into the virtual memory. It's advanced, right? What I'm saying is here is I'm defining this NOP symbol, NOP or no-op, as 0, 0, 0, 0, 0. So when I say no-op, I mean just put 0, 0, 0, 0. And this is the no operation. It does nothing. We have halt, which stops the computer. Load A, which reads an address, goes there and puts that into the A register. Load B, same thing, just for the B register. Load immediate A, which means put the next value in memory into the A register. Load immediate B, same thing. Transfer A to B, self-explanatory, same thing here. Store A, which means get the next value, go to that memory address, and put A there. Store B, same thing. Load A from A, which means take the value in A, put it in memory, get the value, write that back to A. We have an add A and B stored in A. Subtract, same thing. Increment, increase A by 1. Decrement, increase A by 1. Not, which is invert A. And, which is a logical function, or same thing. And then flag, which is copy the flags to the A register. That was actually a pain to figure out. But anyway, we can copy the flags to the A register if you ever want to read them. And here's our branching, so we can jump, which just take the next instruction, go to that address. jump on carry, which means if the carry flag is set, take the next instruction, go to that address, or next value in memory, go to that address. Jump on negative, which same thing for negative. Jump on 0, same thing. Jump negative or 0. If it's negative or 0, jump to that address. Self-explanatory. Store input to A. So we take the value that's currently in this input register, and then we store it into A, and then store A to output. Self-explanatory. We store A to output, and here's our stack function. This is really cool. So we have our stack, which basically is a data structure where we can keep information, but it's really cool. Anyway, so we can push a value to the stack, which just means put something on the stack. A stack is basically like a bucket, and we put something on top, and then we can get it out later. And we keep putting stuff on top, and then we can get it out later. It's a really convenient way to store information temporarily. So anyway, we can push a value to the stack, which just copies A. Let me actually make some comments here. Here, push A to stack, pop, read stack to A. So this just takes the last value on the stack and puts it in A. Call, go to next value as subroutine. So this basically, sorry, fly. Anyway, what this does is it basically says, okay, the next value is an address. That's a function, all right? It's a reusable function. So what we want to do is we want to go there, run some code, and then come back, right, to where we are right now. So this allows me to not repeat code. It's very useful, right? And obviously, if we have the call function, we need the return function, return to from subroutine. And hold on just a second. One moment, please. Anyway, going to continue explanation. So what I've written is a small multiplication program that multiplies any number in just about the most inefficient way possible, but that's okay. It works. I'm proud of it. Very nice. So very simply, we load two values, push them onto the stack. It'll take any value. I'm going to put in 5 into here. I'm going to actually do 4 by 5. It'll multiply it. It'll call multiply, which will multiply those values and put them on the stack, or put the result on the stack, pops it out of the stack, writes it to the out register, and halts. If we go look at the multiply, this supports multiplying by any number. What this does is says, okay, define some address, this address actually, as mplier. So when I say mplier, I'm actually just referring to this address. Same thing for all these. These are just convenient names, so I don't need to actually know the address. And we initialize it with 0. So, and here's where we jump to execution to when we call the multiply. First thing it does, gets the first value off the stack. If it's 0, we can just return right away because the answer is 0. Otherwise, it stores it in the multiplicand. Does the same thing one more time, checks if it's 0. Otherwise, we store it in the multiplier. Then it initializes the product, and it copies the multiplicand to another variable called count because we just want to count. Basically, it's repeated addition or repeated subtraction. Pretty simple. Sorry. And so then it goes here, because we have different code depending on whether the count is positive or negative, right? So we load a count. If it's negative, we jump to multiply negative. Otherwise, we just keep going, and we go here. I'm going to go over the positive one because it's easier. It's how we actually do multiplication normally. So we load, well, it's not, but it's easier, so just whatever. So we load the product into the A register. We load the so this is the running sum, basically, of all the times we've done this. We load the product into the A register. We load the multiplier into the B register. We add those together, and we store that back into the product. Then we load the count, decrement it, and if that's 0, that means we're done. Otherwise, if it's 0, we jump to multiply return, which is the end. Otherwise, we put that back into count, and we jump back up here to multiply positive to do it again. So basically, adds multiplier to itself count times. That's multiplication, right? An inefficient way to do multiplication, but that's multiplication. This thing does the same thing, but just kind of differently because the count is negative. I am recording something. 1 minute, please. Anyway, so then we just have multiply return, which means we just load the product, push it to the stack, return to execution, and undo all these pointers because we're done with them. And So then and then back here, we just pop it off the stack, write it to the out register, and then stop, halt, finish the computer. So I'm going to run this and do some commentary as it's happening. It might go pretty fast, but I can slow it down so we'll just go. All right, it's going pretty slow. All right, so we're loading A with 5. See, that's 5 in binary. We push that to the stack. It's really hard to see, but see, this is now increased by 1. We're loading A with 4. There you go. Pushing into the stack. See, this is now increased by 2. We're calling multiply. So we jump there. See, we pop a value off the stack, which should be 4. So that's in the A register. Perfect. It's not 0, so we skip that. We store that in wherever. Pop another value off the stack. That's going to be 5. Yep. It's not 0, so we skip this instruction. Store it back into some address. See, it's going to jump back there. Load A with 0. There's nothing there. Store that into the product. It's going to jump back up here. There we go. Load A with the multiplicand, which should be 4. Yep. And store that to the count. It's going to jump back up there. Wonderful. So now we're at the multiply branch. We're loading A with count, which is 4. It's not negative, so we're going to keep execution here. Loading A with the product, it's 0. Load B with the multiplier, it's going to be 5. Yep, there you go. Add them together, so this is now 5. Store that to product. Load A with count, which should be 4, so this will go away. Yep. Decrement it, so it's now 3. There you go. It's not 0, so we jump to multiply return. We store the count to somewhere. You see it's jump back up there, and then jump back up to here. I'm going to speed this up because it's just going to be the same thing 3 times. So you see it's going much faster now, but it's doing the same thing fundamentally. See, now the count is 2, I think. Yep, now it's 1. And I'm going to slow it down again. So we're loading the count. Oh, nope. Okay, so we load the count with 1. Decremented is 0. The 0 flag is now set. And boom, we're jumped to this place. We return to execution, or we're about to return execution. Oh, it's pushing into the stack right now. There we go. Return to execution, or to back where we started. It jumps back up here. It writes whatever values in here to the out register, and then it stops. So now you see how even though this is ticking, nothing's happening. That's because this latch is turned off and it blocks this clock signal from propagating, which prevents the computer from going. Now you may ask, is this correct? Great question. Let's pull up my programming calculator. Oops. Well, that's okay. Yeah. So I can show you this was what? 4 times 5. So 4 times 5. It's 14 in hexadecimal. It's 20 in binary or in decimal. And in binary, that'll be 10100. So if we look here, 10100. It multiplied 2 numbers together properly. I cannot begin to tell you how proud I am that I've gotten this to work. I am, hello, there we go. All right, I am so happy. I am beyond happy. This is so cool to me. Wonderful. It's awesome. I think it works. I think everything's perfectly functional. I'm like 90% confident in the fact. I haven't run into problems. Also, the entire instruction space is filled. Like all of these 5 bits, I have instructions for each and every single one, which means there will never be an instruction where the computer just kind of stops and doesn't know what to do. It's always going to do something. It might not be the correct thing, but it'll always do something, either nothing, in which case it'll just increment, or some other weird thing, in which case it'll increment anyway. So that's the short overview of the really cool, it's fine, the computer that I made. This was a learning experience. I really liked it. It was really fun. I'm proud. And I think this is Turing complete. This is absolutely fully 100% Turing complete. I plan to add some like display or something or some cool input because for now it's nothing. It's just manual latches down here. Like I can toggle these if I want. But it's not going to do anything because I haven't written code that reads it. But eventually I want to add like some display so it could actually, display the display any results it wants to onto the output and onto the display, and that'd be really cool. I'll have to write some special driver code for that. That'll be fun. But yeah, awesome. I'm proud. I'm really, actually, truly, greatly happy with this. All right, bye.